it's about implementing the graph data structure and um, running some algorithms on graphs. So we'll be talking about some of the algorithmic stuff using the graphs starting today and kind of going throughout this week. So the project 2 grades are up. Um, so you can check those out. If you have any questions about that, you can message me or the grader on Discord. So really, in a lot of situations, I will just refer you to the grader because I didn't really. If you think that something wasn't done fairly after talking with the grader, then that's kind of when I can take a closer look at it. But as far as partial credit or the way that things were assigned in some sense, like that depends on like the overall scale. And so that's like, I how the specifics of what she took things off for, I may not know, but if you kind of disagree with the ruling after kind of talking with her, you can let me know. So the grader is Tiffany. So Tiffany, so she's in the Discord. So if you go to the channel, um, then let me pull this up. Oh well, okay, she's not online right now, but she posted a message on the Discord. So let me share the screen. So she's been posting in the Discord when she's got the grades done. So grades of Project 2 for Professor Gibson's class is up. So she's online fairly frequently, but so you can shoot her a private message if you have any questions about that. Okay. Okay. Any. Okay. So yeah, just let me know if you have any questions about that. Okay. Okay. So we were talking about graphs. We talked about graph representations, and so in particular, the two main representations that people use and that you should be aware of are the adjacency matrix representation, which basically is just a matrix of Boolean values where it's a two-dimensional array where you have you have a row for each vertex, you have a column for each vertex, and then the entry in that position is 1 if the edge is there and 0 if it's not. So you're kind of for every single possible edge, you're representing with a Boolean value whether or not that edge is there. Okay, and then the adjacency list. And in most applications for a directed graph, we would probably store just the outgoing edges like this. So just the successor list. So this is basically we're saying, okay, A contains edges to C and D, but then in the double adjacency list, you can keep track of your predecessor. So not just what are the edges that point away from you, but also what edges point towards you. So it really depends to where the edge list is advantageous. The only time I could think of why you might want to use an edge list over an adjacency list is if if the total number of edges is a lot smaller than the number of vertices. So for example, what's the disadvantage of adjacent? When would an edge list be better than an adjacency list in terms of total memory? It would only be better in terms of total memory. See, like for for vertex E has no outgoing edges, right? So E is kind of an empty adjacency list, but you still have to store an empty adjacency list, right? So you're still storing something for E to represent, okay, it's just a null pointer here. It doesn't have any edges that point away from it. So yeah, so you'd have to have that. You have to store that there's nothing there. So if for most vertices there's nothing there, you're still going to be storing kind of a blank adjacency list. Whereas an edge list is not storing something for each vertex. It's only storing the edges that are actually there. So if you had like 1,000 vertices in the graph and only 5 edges, then an edge list that stores those 5 edges would be a lot less memory than if you have only 5 edges total over 1,000 vertices. You're going to be storing, you know, at least 995 vertices will have no edges leaving them, right? So you'll be storing a lot of, yeah. So it'd have to be very sparse, exactly, very sparse compared to the number of vertices. Um, but even then, like you still would have a probably a pretty big penalty in terms of the runtime of algorithms, because now if I'm looking for an edge that leaves E, chances are on your edge list it's not even going to be there. So if you're saving a lot on space, you're probably not saving, you're probably losing a lot on runtime, depending on what types of functionality you're wanting to implement. So I mean, you just don't see edge lists hardly ever, I would say. It's almost always going to be in applications an adjacency list, possibly a double adjacency list in the case of a directed graph, um, or an adjacency matrix if you have the memory to be able to hold it. That all comes down to how many vertices are in your graph, and also, right, how many edges in the total graph would you have here. So and like we said at the end of so we're going to talk about the project more in a bit, but we are going to be dealing with the adjacency matrix representation. So you're going to be implementing an adjacency matrix representation of a graph for this next project. Okay. So but it's good to think about it in terms of both representations, because the way you implement the algorithms will be slightly different. So we'll be talking about things kind of in general about, so I might want to consider all of the edges that leave A, for example. That might be for each edge that points away from A, do something. If it's an adjacency matrix, like we said, that's going to be scanning this row in the matrix. But if you had an adjacency list, it's going to be like a linked list. You're going to go to A's adjacency list, and then you're just going to scan the linked list. So the actual C implementation level aspects will be a little bit different depending on which representation you use. But yeah, so the trick is to be able to kind of think about it at a level that's not specific to the actual representation, so that now if I have the representation, I can implement it in whichever way it is. If it's an adjacency matrix, I scan the entire row of A. If it's the adjacency list, you scan the link list, so on and so forth. So we want to keep that in mind when we're thinking about the algorithms. So we're going to start talking now about our first graph algorithm. So this is going to be the this traversal thing. So we talked about this last time, so I'm not going to go too much into it right now, but it's a traversal is basically a way to visit every node in your graph. So just like a traversal in the trees, we had the in order, pre-order, post-order traversals for trees. It was a way of visiting every vertex in the graph. So we could, or in the tree, in the case of a tree. So we performed two different tasks with that. We printed all the details of all of the nodes out. That was one of the applications that we used a traversal for, and the other traversal was to free up all the nodes, right? So we talked about you could visit every single node in the tree and free them, and that's a way to kind of free up all of the memory that is that's inside of your tree. So now we're going to do something similar with graphs. So a traversal should be visiting all of the vertices of the graph. But yeah, so somebody asked a good question. It's not just about finding everything with graphs. It's not just about finding all of the vertices. It's about kind of moving through the graph in some way. So we don't want to just kind of jump around. I don't want to be able to say A, B, E, F, D, C. Just some kind of arbitrary order. We kind of want to explore the vertices according to where the edges kind of lead us, right? So it's like I might start at A and then kind of visit vertices in the graph that are connected to A. And then I might visit, so if I go from A to B, then I might want to visit the vertices that are connected to B. Kind of similarly to like a pre-order traversal kind of moves through the tree in a very strategic way. In order traversals, right? Very specific way. So that's going to kind of be the idea here. So there's two main graph traversal algorithms. So there's the breadth first. So we call it breadth first search or breadth first traversal. I usually call it breadth first search and depth first search. So what are the two? What do we mean by this? So the breadth first search is going to visit all the vertices kind of according to how far away they are from some starting vertex. So we're calling S here is some starting vertex. You're going to start your traversal somewhere. So like with a root, sorry, with a binary search tree, we always started our traversals from the root. But there's not like a well-defined root vertex in a graph. So you can kind of start your traversal from anywhere. So we're going to say that there's some vertex S. You could pick any of these vertices to be S. It doesn't really make, I mean, depending on what you're trying to do, it might make a difference which one you want to start with. But in some sense, you could define it for starting at any vertex. It's almost like you could define any node inside of a tree to be the root somehow, and then start your traversal from that node. That's kind of going to be the idea. So breadth first search kind of visits all of the vertices according to how far away they are from S. So the vertices that are very close to S in terms of the number of edges you have to use to reach that vertex, they're going to be visited first. And then the vertices that have, like, essentially you have to go a long ways. You have to use lots of edges in order to reach them. They're going to kind of show up later in the search. So so for this example, we're going to assume that A is the starting vertex, but again, the starting vertex could have been anything. So if I'm starting my traversal from A is going to be the first vertex in the breadth first search, because basically it's going to be the, it's the only vertex in the graph that uses 0 edges to get to it, right? So starting at A, I need 0 edges to get to A. Okay. Now, next, what I want to do is I want to find all of the vertices that take 1 edge to get to them. So the question is, how many vertices in this graph does it take 1 edge to get from A to that vertex? Okay. And in this case, B, I can go directly from A to B, and I can go directly from A to C. Okay. So actually, I'm going to kind of draw a picture here. So our graph looks like this. So you've got A connecting to B and A connecting to C, and you got E, B connects, oh man, sorry. So you got E, C also connects to E, you got F, so C connects to F, and then you also have D up here. So D connects back to A, B connects to D, D connects to F. Okay, so I'm going to think about these vertices in layers. So this is going to be basically layer 0. So layer is kind of so I call it layers, but so I'll try to explain what this means. So this is layer 0. So you need 0 edges. To reach starting from A. Okay, so the only vertex in the graph, can vertices with no edge pointing to them be reached by traversal? No, they cannot. Yeah, that's a good question. No, they cannot. So any vertex that doesn't have any incoming edges, I mean, it can only be found if you start there. So that could be your starting vertex because you can start kind of anywhere. Yeah, if we started at vertex F without any edges pointing away, then the traversal isn't going to reach everything. So in some sense, we're only going to find the vertices. So okay, that's a good point. So I said we're going to reach all the vertices of the graph. That's not really true. It's you're going to reach all of the vertices that you can reach from your starting point. Okay, so you're going to find only the vertices that you can reach from your starting point. Okay, yeah, that's a good point. That's the better way to describe this. Okay, so layer 0 is all of the edges, all of the vertices that can be reached without needing any edges. So layer 1 is going to be all of the vertices. Layer 1 is going to be basically you need one edge. Man, why does this look so bad? So layer 1 is going to be all of the vertices that have only one edge to them. So from A, I could connect to B with one edge, and with A, I could connect to C with one edge. So these are the only two vertices that are going to be inside of layer 1. So it really is in terms of how many edges away does it take in order to reach that vertex. Okay, so now I still have some vertices that we haven't reached yet. So that's going to be kind of the next layer. So we'll call that, I already used green. Okay, we'll use pink. So layer 2 are going to be the vertices that take two edges to get from. Okay, so basically it's going to be all of the vertices that I haven't kind of visited yet already, or I haven't circled here, that have a direct edge from one of the layer 1 vertices, right? So basically B I can get with one edge. So everything that B connects to that I haven't already circled are going to be the vertices that are in layer 2. So this edge here, right? So I can get to B with one edge, and then I can use this edge from B to get to D in two edges. So that's going to be, so D basically falls inside of layer 2. Also, E falls inside of layer 2 because it can be reached with one edge from B and also one edge from C. But it doesn't matter which one. You just need to have one of them, right? So you can get to B using one edge and then use one edge to get to E. Similarly, you can use one edge to get to C and then use one more edge to get to E. So that still is kind of a path of length too. Because some vertices be in layer 2, you're only assigned to the layer based off of the shortest distance. So yeah, so for example, if we changed the graph so that there was an edge from B to C, then this is a path of length 2 to get to C. You've got this edge to B, and then you've got this edge to C. But because I already had C in layer 1, I'm not going to call it layer 2. It's only in layer 1. Yeah, good question. It's only based off of the shortest distance in terms of the number of edges. Okay, and then similarly, F can be reached with an edge from C. Okay, so layer 2 is going to be consisting basically of everything else because all the remaining vertices are going to be, all of the remaining vertices can be reached with an edge from a vertex in layer 1. So that kind of partitions our vertices into 3 groups. We have layer 0, all of the vertices that can be reached with 0 edges. That's always going to be just your starting point. Okay? And then layer 1, all of the vertices that can be reached with one edge. Okay, where the shortest path is one edge. And then layer 2, where all of the vertices where the shortest path is 2 edges. Okay? And that's going to be everything. Okay. And so now, essentially what a breadth first search traversal is going to do is it's going to visit all of the vertices of layer 0. In this case, it's just A. So it's going to visit all of the vertices of layer 0. So that'll be A. And then it visits all of the vertices in layer 1, and the order doesn't really matter. So I could do it in either order. I could do C, then B, or I could do B, then C. The order doesn't really make a difference here. The it doesn't matter how you break ties inside of, yeah, there can only be one vertex in layer 0. There can only be one, it's going to be whatever vertex you're starting from. That's the only one that can be in your starting group. So you're always going to start, the first vertex will always be the first one that you start. Then the next vertex will be all of the vertices in layer 1. There might be only one, there might be 0. In the case of vertex F, right, if we were to have started our traversal from vertex F, then layer 1 would actually have no vertices in it because there's no edges that go away from it. And that basically would be when you're done. Okay? So layer 1 has some number of vertices in it, and you can visit them in any order. And then you get to the vertices in layer 2, and you can visit them in any order. It makes no difference. So this could be E, D, F, or something like this, right? So, right. So, like this is an example of a breadth first search. So you're visiting the vertices according to these layers. You can break the ties inside of a layer in any way. The example that is in the notes breaks the ties in alphabetical order. So, um, so the way that the ties are being broken here are basically in alphabetical order. Layer 1 is B and C, so he's breaking the tie in alphabetical order. So B first, then C. And then the layer 2 is D, E, and F, and so then again, the ties are being broken D, E, and F. But the reality is that this is the idea is in order for it to be a proper breadth first search, it makes no difference in how you break ties. If two vertices are inside the same layer, the order in which you visit them doesn't matter. But if you have a vertex inside of layer 1 and another vertex inside of layer 2, you must visit the vertex in layer 1 before you visit the vertex in layer 2. Okay? And that, of course, generalizes. So you keep going until you have no more vertices in your next layer. So basically, at this point, there's no vertices in layer 3, and so that's when we would be done. So here, if we started the traversal from F, F would be layer 0. There would be no vertices in layer 1, and so then you'd be done. So the breadth first traversal would basically just be F by itself. That'd be it. Okay? Any questions about that? So we'll talk about how you implement it, but the important thing is how does the traversal work? Is there a way to know that you visited all the vertices in the graph? So, okay, yeah, so, right, if you want to know, did I find everything? So one thing you could do is count the number of vertices. Usually a graph will know how many vertices are in the graph. So if you know how many vertices there are, you can count them all. You can count the number of them that you visit and see if that count is equal to the total number of vertices in the graph. One way that so a lot of times what we'll do is we'll have a visited array. So we'll have like a Boolean for each, we'll have a Boolean variable for each vertex, and we'll say true or false, have I visited this vertex? So initially everybody's false, and then once you visit the vertex, you set its value to true. And so then you would know if you visited every vertex, if every single vertex had its visited variable set to true. So that's an example of a way that we might do that. So yeah, you definitely can keep track of that if you want to know. Okay. So breadth first search is being really careful about the order in which in the distance a vertex is from your starting vertex, wherever you're starting. Okay, and you can start from any vertex you want, but then once you start, you need to be visiting vertices only in the order from which how far away they are from from uh, from your starting vertex. Depth first search is kind of the opposite in some sense. It's not really trying to get a long ways away, but the behavior of it tends to get a long ways away from your starting point fast. And then it will kind of back up and find things that it missed or something. So so that's what this is saying. Visit all vertices as far away as possible before kind of backing up. So essentially, we start. So the idea behind depth first search is you just find some vertex that you haven't visited. So let's here So I'll copy and paste a new copy of the graph here and then clean this up. Because there's no notion of layers in depth first search. So breadth, this whole notion of layers is only specific to breadth first search. So depth first search, the idea is, okay, we're going to start with we're going to have our starting point, and I'm going to kind of, oh, it's because I'm in pen. Okay, yeah, here we go. So I'm gonna put a check mark next to it once I visit it. Now, what a depth first search is going to do is it's going to find an edge that leaves your current vertex, your starting vertex, and it's going to look at that vertex and it's going to ask, have I already visited that vertex? And if I haven't already visited that vertex, then you're going to visit it right now. So basically, we're going to move from A to B. So we're at A, and then I'm going to move to B, and I'm going to mark B as being visited. And then I'm going to look, okay, so to make it consistent with the notes above, I'm going to delete that edge again. That was just to talk about, yeah, the situation with the layers and breadth first search. But to make it match this, I'm going to delete that edge. Okay, so I'm currently at B, and now I'm just looking for the first edge that leaves B. So the first edge that leaves B is this edge to D. And now the question is, have I already visited that vertex, right? So the idea would be like we'll have a set of Boolean value, a Boolean for each variable, and if we visited it, we'll know if we visited it or not. So in this case, I'll see I haven't visited this yet, so then I move to it. So I'm just going to go ahead and move directly from B to D, and I'm going to mark it as being visited. And now I'm looking for the first edge that leaves D. I'm looking for the first edge that leaves D, and that's A, exactly. And so now the question is, have I already visited it? Have I already been there? And so, I've put a check mark here to denote that we have. In the code, we would have kind of an array that's storing a Boolean value for A, and we'd be able to see, okay, yes, we've already visited it. So you don't revisit it. Okay, so we're not gonna visit a vertex if we've already visited it. So then I go on to the next edge that leaves D. So the next edge that leaves D is F. Okay, and now the question is, have we already visited F? And we haven't. So that's going to be the next one we go to. So I'm going to go ahead and move from D to F and mark it as being visited, right? And so you can see now, like, we're currently at F. Like, I'm currently visiting F. And F is definitely farther away from A than C is, right? But so in a depth first search, sorry, in a breadth first search, we would have, in the previous search, we would have wanted to make sure the C came before F. But in this case, we're visiting F before we get to C. Okay, now I'm checking for outgoing edges for F, and F does not have any outgoing edges. So there's no, you like this way better. There's times where you want to use both. So which one you want to actually use depends on what it is you're trying to do. So yeah, exactly. So this way works recursively. So we're going to kind of talk about this here in a bit. The first traversal kind of works like a first in, first out, like a queue. And in fact, it is implemented with the queue data structure. Whereas this implementation is can be done recursively or with stacks, right? So recursion and stacks kind of go hand in hand in some sense. This last in, first out. So this is this could be implemented with a stack or with recursion, whereas this one is implemented with a queue. And so it's kind of a nice kind of flip side between these two data structures that we've seen. So again, we'll talk about the actual implementation here in a bit. But right, so now the idea is F has nowhere to go. So now we're going to basically back up to where it came from. Who called F, right? So we marked it in green. D called F. So the idea is we're going to go back to D and we're going to see, okay, does D have any other edges that we can get to? And we'll try to visit more vertices from D if we can. But D has no other outgoing edges. So D is kind of done, and we're going to back up to wherever we call D from. So we call D from B. So we're going to back up according to this green edge here, right? So we go back to B, and now we continue where we left off. So B, B checked this edge to D, and so now I see that we've got this edge to E. So now the question is, have we already visited this vertex? And we have not visited this vertex, so I'm going to go ahead and mark it as being visited. And we'll go ahead and move to it according to this edge. E has no outgoing edges, so there's nowhere to go, so we're just going to backtrack to B. And now B has no other outgoing edges, so then we backtrack to where it came from. That was A. And now A, does it have any more outgoing edges? And it does, right? So A has this outgoing edge to C, and oops, and C has not yet been visited, so we will visit it now. We mark it as being visited. C's outgoing edges basically are only two vertices that have already been visited. So E and F have both been visited. So C is going to be done. So we're going to backtrack to A. A is going to have no more outgoing edges, and then that's basically going to be when we're done, right? So A was our starting point, and A, we backtrack to A, and A has no other outgoing edges, and so then basically we're going to be done. So the order in which we visited them, what was the order we visited them, right? So we were at A first, then we went to B, then we went up to D, then we went over to F, and then we backtracked to D, then backtracked to B, and then so make sure that's, then we went over to E, then we went back to B, back to A, and then we went back down to C. All right, so this is what is written in the notes, A, B, D, F, E, C, but that's where this kind of comes from. That's the order in which we visited them, A, B, D, F, E, C. So this is just kind of blindly going through, exploring paths in the tree, in the graph. Sorry, that's a bad habit. I don't know why I keep saying that. So yeah, obviously this is a graph. It's not a tree. We're kind of blindly walking through the graph, and it tends to have this behavior where you'll get a long ways away from your starting point, and then you'll kind of backtrack and then get farther away, backtrack, get farther away, backtrack, get farther away, until you basically have nowhere else to go. And that's how you kind of explore everything. So that's why it's called depth first. So the idea is you explore the depths of the graph first, whereas breadth first somehow kind of makes sure that you visit everything nearby first, and then you get a little bit farther away, then you get a little bit farther away, then you get a little bit farther away. Those are the two different traversals. Are there any questions on this? Okay. So the so what issue can impact these algorithms? Okay, yeah. Yeah, that's a good question. So what are the advantages and what are the disadvantages? So Project 4, basically what Project 4 is going to be doing is going to be computing shortest paths. And if you want to compute a shortest path, you can, okay. So it's going to be shortest paths in kind of, yeah, exactly. You need breadth first search to compute shortest paths, because depth first search, the way it finds vertices, it could take a really long path to find a vertex. So for example, your graph could look like this. You could have your starting point A be here. You could have B be here. You could have C be here. And A might connect directly to C, but B could have some really long path that eventually gets back to C, right? So a depth first search in this scenario would go all the way around to C this way, taking this really long path to get to C, whereas I could have just kind of directly gone to C. So that's an advantage and a disadvantage to breadth first search, right? If the goal is to explore, then you want depth first search, right? So if you're trying to kind of figure out, look for something that maybe is a long ways away from your starting vertex, you kind of want to go a long ways away from it. But if the goal is to compute a shortest path, then you definitely want to use breadth first search. So that's one example of an advantage of one versus the other. So the reality is, it comes down to, what are you trying to do? What do you want to So are you trying to print the contents of the graph? Are you trying to compute shortest paths? Are you trying to free up all the vertices in the graph? Are you like, what are you trying to do? Why are you trying to visit all of the vertices? What are you trying to accomplish with this traversal? Then you want to think about, okay, which of the two is going to be better for me? So there, here's shortest paths is a clear example where you got to use breadth first search. Depth first search is probably going to be pretty bad if the goal is to compute short paths. I do want to remark that when I'm talking about short paths, I mean short paths in terms of the number of edges. If we have a weighted scenario like we had here, like in this airport scenario, where you have weights you have numbers on the edges that represent how far apart they are. One edge might be really long. Like it might be or it might be really expensive or something. Like if I go directly, okay, yeah, that's a good question too. Why? Oh, my pen's upside down. That's why. It could be that all of these edges weigh 1, and it adds up to not being too much. And this might have a value 1 million or something. 100,000. Right? So taking this one edge that's really costly might be bad. So breadth first search is not a good algorithm for shortest paths if you have weights on these edges. It's only if you're essentially trying to minimize the total number of edges. But don't worry, there's other algorithms to compute shortest paths in this scenario as well. Okay, Zachary's question. So how would you assign values to edges if you want to have weights on the edges? So if it depends on your representation. If you have an adjacency matrix, then oftentimes what you'll do is instead of having a 1 here, you'll just have it be the weight. So instead of this being, like if this edge from A to C has a weight of 50, then maybe I'd just put 50 here. So it'd be an integer array, and maybe I would just put the value 50. So basically, if it's 0, that means the edge is not there. And if it's something that's not 0, then that would mean that there's an edge, and the number that's written there is the weight on that edge. Yeah. So 0 would mean no outgoing edge. Exactly. Exactly. And then in an adjacency list, you could basically have this be a struct I mean, it is a struct, right? So right now it's only storing the vertex, essentially, that you're connecting to. But you could then also add inside of the struct a variable to store the weight. Okay? Okay. Okay, so I want to talk a little bit about the project so that you can, so that when this pops up, if you want to start implementing the bare bones like graph stuff, you'll be able to do that. Oops, that is the one I just had up. So we're going to come back. So this is here. There's some pseudocode to implement the depth first search. So this is actually showing, yeah. So this is showing it a recursive implementation of depth first search, and it's showing kind of a iterative approach that uses a queue for breadth first search. So if you want to get a little bit ahead, you can look at that. But so I'll come back to that. We'll talk about this on Wednesday. Okay, so actually, did I have that there? All right, graph.h. So I want to show you graph.h. So this is basically what your graph.h file is going to be looking like. So I get questions on some of these things. Sometimes I have a function in here and we didn't call the function in the project. Is that okay? And the answer is yes. The goal here is two things: to implement kind of a full functioned data structure that could be used for lots of different projects. But then secondly is going to be to implement like a project that's going to actually use that data structure. So some of these functions, it might, excuse me, it might work, you might call all the functions, you might not, but I still want you to implement them because they're kind of a standard thing in a general graph data structure. Okay, so an edge. So a vertex is basically just an integer. Is that not being, that's not being defined here. I defined that in the queue, I think. But a vertex is so a vertex is basically just an integer. So we're type defing a vertex to just basically be an integer. So an edge is basically going to store two things. The from vertex, that's the tail end of the edge. So if you have an edge in a graph, oops. So like if I have A connecting to B, then this is the from vertex, because the vertex starts at A. This edge is going from A to B. Or again, so if in the code, we're not going to use letters, we're going to use numbers. So if this is like going from vertex 0 to vertex 5, then this would be a struct that looks like this. So the from vertex would be 0, the to vertex, the to vertex is going to be 5. So this is the way it'll be represented. So it's just a pair of integers. So, I could say, I could call this like, I could create this edge like this. Man. Edge, my edge. So this would be like the use in main. And then I say my edge dot from vertex equals 0. My edge dot to vertex equals 5. Okay, so you can just define an edge variable inside of main. Then you can set the dot from vertex to be wherever you want the edge to start from, and the to vertex will be wherever you want it to end up. Okay, so that's for an edge. Then for the actual graph itself, it's going to basically store two things. It's going to know the size of the graph, so n's the number of vertices in the graph. So graphs are usually, not always, but it gets a little bit tricky. Yeah, so oftentimes graphs are viewed as kind of static data structures where you're not going to be inserting and deleting over time. So we're going to kind of implement it that way. We're going to assume that we know the entire graph at the very beginning, and we don't need to insert or delete a vertex from our graph like we were with the binary search tree. So we're going to know the number of vertices of the graph. We're going to know that right at the beginning, right? Which, again, like if you were going to implement shortest paths on San Antonio's road network to try to compute the shortest path between 2 points in San Antonio, then you would know how many vertices are in that graph from the start. Of course, you might have to make updates to it over time in an actual application, but you get the point. Like there's kind of a static snapshot, and we're trying to compute something on that. And then it's going to be an adjacency matrix. So again, we're not going to be dealing with weights in this project. So it's basically going to be a two-dimensional array of booleans. It's going to kind of be the idea, but there's no boolean, so that's why it looks like an integer array. You want to save vertex information in a matrix or a list, and on top of it, it's edge information. So we're going to be storing an adjacency matrix. So it's going to look like this, although there won't be weights. So it'll either be ones or zeros. Okay, so it's going to be ones or zeros. So basically, if you have 10 vertices in the graph, it's going to be a 10 by 10 matrix. So then I know vertex zeros, the edges leaving vertex 0 will be stored in this row. The edges leaving vertex 1 will be stored in this row, and so on. Does that make sense? So Zongshu is going to be doing a lot of this stuff in class. He's going to be, oh, okay. So okay, yeah. So let me keep moving along here. So when you create a new graph, you're going to be passed as a parameter the number of vertices. Then you'll get a two-dimensional array here. Initially, you're going to initialize all of the edges to being empty. So initially, you're going to just basically set all of the edges as not being there, and then kind of one at a time, we're going to add the edge. So I might say, so inside of main, I'm going to do, again, it's upside down, graph, my graph, equals new graph. I'm going to pass it the number of vertices. So maybe it'll be like 100 or something. If there's 100 vertices in my graph, this is going to be the number of vertices in the graph. So this will return for me. Yeah, exactly. Exactly. So then there's going to be an add edge function. So I'm going to be able to say add edge. I'm going to pass it my graph and my edge. And then this function is basically going to see, okay, we want to add an edge from vertex 0 to vertex 5. So then in this matrix, you're going to go from index 0 to index 5. 1, 2, 3, 4, 5. 0, 1, 2, 3, 4. Okay, we don't have it here, but you get the point. So you'll go to row 0, column 5, and flip that number from 0 to 1. That's basically going to be the idea. So then you can implement all this stuff and get a start on that. So there's some other functions that are basically, there's going to be some functions that we're going to use to kind of scan all the edges that leave a vertex, and then we're going to have this shortest path function that you're going to implement that's going to be based off of this breadth first search traversal that we just talked about in class today. Okay, so we'll be talking about breadth first search on yeah. Okay, yeah. So for the file, let me show you the file. So it'll be clearly defined in the instructions, but the first line is going to be the number of vertices in the graph. So you'll instantly know how many vertices are in the graph. So you can read in the number of vertices, and you can just create a graph with that number of vertices. Then the next line is the number of edges. So then you can then loop through that number of times. This is basically the endpoint of the edges. So this is the from vertex and the to vertex for each of the vertices in the graph. Okay, so we'll say we're going to add an edge from 0 to 1, 0 to 3, 1 to 2. So it's basically telling you what are all the edges that you should add to your graph. And then this is telling you how many shortest paths do we want to compute. So then this is basically going to be compute the shortest path from vertex 0 to vertex 8, and from vertex 2 to vertex 6, and 7 to 6, and 3 to 7, so on and so forth. That's basically what the project is going to be. Okay? Any questions on that? I'm sure there will be more once you get it, but that's the high-level idea. So Zhongshu in recitation this week, yes, you're going to print out the sequence of vertices that you would visit. Go from 0 to this vertex to this vertex. Exactly. You're going to be printing out the path. So Zhongshu in recitation is going to be going over kind of some of the fundamental how to build a graph and get some of this basic functionality implemented. And we'll be talking more kind of project-based stuff, the algorithms behind it. The actual vertex or just ints. So what's being stored inside the matrix is just going to be like a 0 or 1 if it's there. So it would be like, so if I want to know, is there an edge from 2 to 6, like if I want to ask this, I would implement this like this. I would say if, so it's my graph is the variable, if my graph arrow adjacency M, right? That's the name of our adjacency matrix variable. If this of 2, 6, so I could just put this, or I could say double equals 1. Like if it's equal to 1, then, you know, whatever. So in here, you would have code that would only exist if there's an edge from 2 to 6. So basically, you can. So does that make sense? So if I want to check this edge, you just put the vertices of the edge you're considering as the indices of the adjacency matrix, and then you're going to check to see like is that 1 or not. Okay. Any other questions? Okay, that's all then. Thanks everybody. We will see you all on Wednesday. Have a good one.